Hello everyone, thank you for attending my talk. My name is Emese Vegh. Our title is The Use of Physicochemical Changes to Address Late Postmortem Interval in Unburnt and Burnt Bones. A bit of an overview for this talk. First, we'll look at the rationale behind the study with a bit of an introduction to burning. Then we'll move on to the research questions, the experimental outline, and the methods, and then the results. I start with burning. As we know, one of the most challenging tasks that archaeologists face is analyzing burnt human remains. The bone is left variably fragmented, warped, discolored, shrank after the fire event. The purpose of burning can be the destruction of the body, homicide or suicide. There can be accidental fires as well, which result in the death of the victims, such as wildfires or building fires. The two most important factors are the heating temperature and the duration of the heat. Bone goes through a series of changes through burning, such as color change, warping, fragmentation, and shrinkage. Burning of the body can happen either when the body is fully flesh or once it had decomposed to different degrees. Early studies mainly focused on establishing whether the bones were fresh or dry when burned. The techniques used were primarily microscopic techniques based on the presence of thumbnail fractures and warping, but later it was concluded that these fractures did not depend on the presence of soft tissue on bone, but rather the amount and distribution of collagen retained in bones. Since these fractures can be present on bones that can be as old as 100 years, these heat-induced fractures are not reliable indicators of fresh bone. In an archaeological context, human remains might have been cremated at a later date, not right after death, due to, for example, funerary rites and post-processing of the dead. In some cases, for example, at some tombs in Neolithic and Bronze Age Ireland, excavators suspected that human remains were either passively or actively excavated before inhumation and cremation. Similar problems come up in forensic anthropology. At the crime scene, it is imperial to know when the body was burned compared to the time of death. There are a few cases discussed in the literature where a single individual has been found partially burnt. In these cases, the PMI was established based on carnival gnawing and pattern thermal destruction. Therefore, to address this clear gap in the literature, the research question of this study is, can we tell if bones were fresh or decomposed at the time of burning? I tried to answer this question by setting up an actualistic taphonomy experiment and then examining the structure and the elemental concentration of the bones pre and post burning. So the experiment looked like this. First, fleshed pig TBA were placed in a cage on a field in Whiten Woods, Oxfordshire. This was done in several rounds. Then the legs were left to decay, collected, and subsequently burnt after 2 weeks, 1, 3, 6 months, and after a year. Additionally, fresh fleshed legs served as unburnt and burnt control samples. The bones were burnt until they turned mostly white or calcined. The average mean temperature of the fires were 553 degrees, and the mean high temperature was 751 degrees throughout the burns. These temperatures were bone temperatures recorded by a thermocouple and not fire temperatures. Fire temperatures at the fire's hottest point reached 995 degrees, and each fire lasted for an average of 2.5 hours. To address this question of whether the bones were burned fresh or decomposed, I attempted two methods in this paper. So the first one was investigating the structural changes by Fourier transform infrared spectroscopy, or FTIR. Spoiler alert, this was great at distinguishing between unburnt and burnt bones, but was not helpful answering our question. The second one was elemental concentration measured by the wavelength dispersive detector of the electron microprobe. This one actually gave me results which can inform on the postmortem interval. Actually, I attempted other methods as well, such as histology, using microbial bioerosion features in burnt bones, but it wasn't successful, and we found that burning can produce bioerosion-looking features. So, although we'll be focusing on the microprobe results, first I want to show quickly what the structural changes tell us. So FTIR was used to retrieve structural and molecular information from the unburnt and the burnt bones. The two spectra on the left shows the bone vibrations, The upper image shows the mean unburned bones, and the lower spectra shows the mean burnt bones. The different colors correspond to different postmortem intervals. Changes were recorded in unburned bones during the first year of postmortem interval. These changes were crystallinity increase and carbonate loss, which were both statistically significant in unburned bones, and this change has been documented in previous studies as well. But burning seems to override these early genetic changes, and this is because fire drastically changes the structural profile of bones, including its crystallinity and carbonate content. Linear discriminant analysis, or LDA, was performed at the FTIR dataset. It was successful at differentiating between unburnt and burnt bones, as you can see on the graph. The most important contributors to this separation were the different carbonate to phosphate ratios. However, none of the statistical methods could differentiate between the postmortem interval groups on burnt bones. Now let's move on to the electron microprobe results. I won't bore you with the lengthy preparation process for this technique, but it took months just to prepare the samples to be placed into the microprobe. So just a little background to bones elemental concentration. Hydroxylapatite is the basis of all biologically formed apatite, while bioapatite is a carbonate-containing variety of hydroxylapatite, which forms the inorganic component of bones. As you can see from its formula, bioapatite is chemically more complex than hydroxylapatite because it can incorporate a wide variety of elements into its structure, which are detectable as trace elements by the microprobe. It is especially susceptible to changes during burning. For this analysis, other than the experimental bones, I also used 2 cremated human remains from Kiltierney, which is a Neolithic site in Northern Ireland. These 2 fragments were identifiably different from different individuals. One of them presented a thumbnail fracture, so the implication here is that these bones were burnt relatively flash. But as I said before, thumbnail fractures are unreliable indicators of bones burnt at the fresh state. Points of measurements were taken from the outer cortical layer, the midcortical region, inner cortical layer, and around vascular canals on the transverse bone sections. A total of 670 points were used for the analysis, with 11 elements measured. So these elements that were measured were calcium, phosphorus, sodium, chlorine, potassium, iron, aluminium, silicon, strontium, manganese, and magnesium. This figure shows the changes in the different elements abundance in the unburnt and burnt bones as a function of time. So the x-axis is the postmortem interval, or time since deposition, and the y-axis indicates the concentration of the specific element. The blue line indicates unburnt bones, while the red line shows the burnt bones. The shading around shows their variation across samples in ±2 standard error. The high values of elements in the fresh burnt bones compared to the unburnt bones indicate organic loss and not an actual increase in the elements. The coefficient of variation was low in most of the elements. When unburnt and burnt bones were compared, calcium, phosphorus, iron, aluminium, silicon, and strontium change through time in the same fashion, suggesting that these elements are not highly affected by burning at our temperatures, which were a maximum of 750 degrees. Iron, aluminium, silicon, and strontium are not affected by time either, which was shown by multivariate comparison of means testing. The only elements of interest to the study were potassium, sodium, magnesium, and chlorine, which changed significantly with the postmortem interval. So we will be focusing on potassium from now on. This graph shows the potassium decrease in the different areas of the bone cross-section as a function of time. So the x-axis is the PMI here as well. Unburned bones are up, burnt are down. Linear regression results show that potassium was the only element that decreased in both unburnt and burnt bones with time in all areas. Multivariate comparison testing showed that all fresh bones were significantly different from all other postmortem groups. There was a rapid decrease of potassium levels after 2 weeks, after which it steadily decreased in both unburnt and burnt bones. After 3 months, the potassium concentration in the Inner and mid-cortical areas, as well as around vascular canals, were under 0.06 weight percentage, while slightly higher in the outer cortical zones due to exogenous potassium contamination from the soil. Thus, potassium levels were never above 0.06 weight percent after 3 months post-mortem in the inner and mid-cortical regions, as well as around vascular canals. It makes sense that potassium decreases since it is found in the extracellular fluid in the body, and its decrease signifies dehydration of the bones. The most important finding here is that potassium values survive burning, and its decrease might be possible to be used as an indication of whether the bones were fresh or decomposed at the time of burning in modern bones. Potassium was previously found to be localized in the removed organic bone material in another study and was suggested to be present mainly in a labile state. But the fact that organic material was removed by burning in the present study, but potassium was detectable by the microprobe in the thermally transformed bioapatite, makes it possible that potassium may be chemically bound to the crystal. LDA analysis was successful at clustering unburned and burned bones from the elemental concentrational data set as well. Let's move on to the archaeological cremated bones. These figures show the elemental concentration of the measured elements in the Neolithic cremated human remains. Each graph shows a different element. The different colored bars indicate different areas of the bone cross-section. The outer cortical layer showed the highest variation in elements, followed by the areas around vascular canals. Many elements were hardly or not at all detectable in the mid-cortical section in these bones, while the levels of these elements were high in the outer cortical layer. The mid-cortical area shows the lowest variation, suggesting the least amount of contaminants from the environment. Calcium and phosphate molar ratios were similar to values of the experimental bones in both the unburned and burned bones. The fact that this ratio didn't change significantly with burning or diagenesis suggests that this ratio stays a characteristic signature of bone. These elements display very high values in the outer cortical zone, but not in other areas, suggesting diffusion of exogenous elements from the soil. Exogenous potassium from the soil diffused into the outer cortical layers and to a lesser degree from the inner cortical end and through the vascular canals. There is no detectable potassium in the mid-cortical layer, which suggests endogenous potassium has depleted. After burning, the bone's crystal structure should be stable and no changes should happen post-burning due to its increased crystallinity. This might mean that potassium essentially depleted in the Neolithic samples prior to cremation. Therefore, these bodies might have been left to decompose prior to cremation to a degree that endogenous potassium was no longer present. Okay, so let's sum up the findings. The first conclusion is that burning overrides crystallinity increase and the loss of carbonate, which happened in the first 1 year post-mortem. Calcium, phosphorus, iron, aluminium, silicon, and strontium were not significantly affected by burning at maximum of 750 degrees. Iron, aluminium, silicon, and strontium were not associated with time either in the first 1 year post-mortem interval. Magnesium showed a non-uniform and non-linear increase through time in the burnt bones. Only 3 elements were found to be linearly affected by time since deposition in burnt bones, which were potassium, sodium, and chlorine. Potassium levels of under 0.07 weight percent in the mid-cortical zones of burnt bones suggest that the corpse was not burnt immediately after death, but after 3 months. I have to note, though, that these bones were surface exposed, so in case of buried bones, the dehydration might be slower. The plus minus 17.22% is the analytical error of the instrument calculated from the secondary standards. In the Neolithic bones in this study, the endogenous potassium levels measured from the mid-cortical areas were below detection limit of the microprobe, which is 0.01 weight%. Since bone crystal structure should be stable after burning, the logical conclusion from this is that these bodies were left to decompose prior to cremation. Based on the experimental results of this study, the PMI before burning might have been over a year. Overall, to answer our question whether we can tell if bones are fresh or decomposed at the time of burning, the answer is yes. Elemental measurements of potassium values can or might indicate whether bones were burned in a fresh or decomposed state. Thank you very much for your attention.